Hey everyone, this is the introductory video to the electrochemistry unit. As you may have guessed, electrochemistry is the chemistry that involves electricity. It is the chemistry of batteries. It's also the chemistry of electroplating, which is the non-spontaneous direction in which electrons normally want to flow. You'll be taking all of your notes, probably on this handout here from class, in which we have all of the different types of electrochemistry. It also talks about what voltage is, as well as how it relates to free energy, the spontaneity of a chemical reaction. We also have your handout which talks about the voltage potential and how it relates to the equilibrium constant for a given chemical reaction. We have a section on galvanic cells, which describe batteries. It's another word for batteries. This is the spontaneous flow of electrons. We have electrolytic cells, which are not batteries. In fact, the electrolytic cells are using energy from an outside source, for example, an outlet, to drive a non-spontaneous chemical reaction, such as electroplating, and we'll talk more about what that is later. The basic premise of electrochemistry is that you're linking together two different substances. If you link together a substance that is willing and able to lose electrons, such as magnesium, along with another substance which will readily gain electrons, another metal perhaps, such as copper 2+ in the aqueous form, and you connect them with a wire, the electrons will flow from the direction of the substance which will readily lose the electrons to the substance which will gain electrons. Now you may be asking yourself, copper, isn't it more stable in the copper 2+ state than in the copper solid state? Why would you even get copper 2+ in the first place if it wasn't somewhat stable? And the answer is copper 2+ is in fact quite stable. What it comes down to is really, since these are both metals, who wants to lose more? So it's not really like the copper 2+ is just dying to gain electrons. Instead, it becomes a little bit of a who wants to lose the electrons more of a battle. And in this case, because magnesium is a group 2 metal and copper is a transition metal, because group 2 metals will lose electrons more readily, it will be a spontaneous reaction in which the electrons will flow. When you separate these two substances by a wire, you get electricity flowing through the wire in the direction of spontaneity, from the substance which will lose electrons more readily to the substance which will gain them a little more readily. And you don't have to ever really know which of these two is going to happen in terms of who's going to pull more. You don't have to know that in your head. Instead, you'll be provided something like this. Now, the AP exam used to give you this entire table of what are called reduction potentials. Instead, they will likely not give you the entire table, but will only show you the substances that you need. So you'll only see one or two of these at a time, which in many ways makes this process a lot easier to navigate. I want to talk a little bit about how you read this table to begin with. The reason why it's called a reduction table is because all of these are shown from the direction of reduction. As you remember from previous units, oxidation is the loss of electrons, reduction is the gain. Notice that all of these are shown from the perspective of gaining electrons. That's why it's called a reduction potential table. This E right here, capital E, is the reduction potential, and it has units of volts. I know that you've heard of volts before. You can think of volts as potential energy for electricity. Meaning, just like gravitational potential energy is greater for a ball on top of a large hill that is going to roll down to the bottom, the gravitational potential energy is greater for the ball on top of a large hill than it is for a ball on top of a small hill. Electron potential is very similar. It's not identical, but the analogy still holds true. When you see a large number here, that implies a large hill. When you see a small number, that might imply a small hill, with the exception of the positive negatives. Notice that in this case, you'd only talk about positives. However, this whole positive-negative spread is going to give us a little more difficulty if you don't learn how to orient yourself. When I look at this, I see lithium plus electron, and it's the lithium ion. And I see this large and negative. On the other end, I see something like fluorine plus 2 electrons. When I see this, I should say to myself, fluorine in the neutral state is a much stronger puller of electrons. Positive electron volts means spontaneous. Lithium solid is the one that's going to want to lose electrons readily. So gaining electrons back from the ion to become lithium neutral is highly negative, meaning not favorable. That's how you read this table, and this ends the first video for this series.